Your hand is resting on a table. The meeting starts in 10 minutes. You glance at the wall clock, 2:50 p.m, and think, I still have time. But what if I told you that thought is wrong? Not because you miscounted the minutes, but because the meeting at 3 p.m. doesn't start in 10 minutes. It already exists. The moment you walk through that door, the moment your colleague asks where you've been, the moment you apologize for being late, all of it sits, fixed and unchangeable, at a specific point in space-time. You cannot arrive before it or after it in any absolute sense, because before and after depend entirely on how fast you're moving and where you stand. This is the problem of punctuality in a block universe, and it reaches all the way down to whether time has an edge at all. The name for the question is temporal finitism. Does time have a boundary, a beginning, an end? Woven into that question is another. If the universe is a four-dimensional structure where past, present, and future are equally real, what does it mean to be late? Philosophers call this view Eternalism, and its most vivid form is the block universe, a static, unchanging spacetime in which your entire life, from birth to death, is already laid out like a thread frozen in ice. Walk faster, and you don't change when you arrive. You change which slice of spacetime you call now. The meeting doesn't wait for you. You and the meeting are both fixed points, and the only question is whether your world line, the path you trace through spacetime, intersects the meeting's world line at the right coordinates. Here is the part that shocks. Two people standing next to each other, moving at ordinary walking speed in opposite directions, can disagree about what is happening right now in the Andromeda galaxy, not by seconds, but by days. Roughly 3 to 6 days, depending on how fast they move. That shift is not a trick of perception. It is a direct consequence of special relativity, confirmed in every particle accelerator and GPS satellite, and it means there is no single cosmic now that everyone shares. If simultaneity, the idea that two events happen at the same time, is observer-dependent, then so is the future. One person's not yet is another person's already happened. The deeper you look, the stranger it gets. Lift a clock 33 centimeters, about 1 foot, and it ticks faster than a clock on the floor by a measurable amount. Your head ages faster than your feet. The effect is tiny, roughly 90 billionths of a second over a lifetime, but it is real, measured, and confirmed by atomic clocks in Boulder, Colorado, in 2010. By 2022, physicists resolved gravitational time dilation across a distance of 1 millimeter, the width of a pencil tip. If when depends on where you are and how fast you're going, then the idea of a universal clock counting down to the meeting collapses. There is no clock. There are only paths. And if you ask the best equation we have for the universe as a whole, the Wheeler-DeWitt equation, when the meeting happens, the equation has no answer. It contains no time variable at all. The wave function of the universe does not evolve. It simply is. A meeting is scheduled for 3 p.m. in a conference room 3 blocks away. You check your watch, 2:52, 8 minutes. You imagine the meeting as something waiting in the future, an event that has not yet occurred, and you picture yourself traveling through time toward it. If you walk quickly, you will arrive before it starts. If you walk slowly, you will arrive after. Being on time, in this picture, is a race between you and the future, a test of whether you can reach the event before the clock on the wall ticks past the agreed-upon moment. That picture feels obvious. It is the picture we live in, but it is not the picture physics gives us. In 1908, a German mathematician named Hermann Minkowski stood before an audience in Cologne and said, "Henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." He was not speaking metaphorically. He was describing the geometry Albert Einstein had uncovered 3 years earlier in special relativity. Einstein had shown that the speed of light is the same for every observer, no matter how they move. That simple fact, confirmed in every experiment since, forces a trade. If light's speed is fixed, then time and space must be flexible. Two observers moving relative to each other will measure different elapsed times for the same pair of events. They will disagree about which distant events are simultaneous, and there is no experiment that can settle who is right, because both are. Minkowski took that insight and reformulated it geometrically. Space and time are not separate. They are two aspects of a single four-dimensional structure called spacetime. Events are points in that structure, and objects trace curves through it called worldlines. Your life is not a sequence of moments. It is a continuous path from birth to death, a thread woven into the fabric of spacetime. The meeting is not a future event waiting to happen. It is a point, a fixed location in spacetime. And the question of whether you are late is simply the question of whether your world line intersects the meeting's world line at the coordinates everyone agreed on. This is not philosophy. This is geometry. And the geometry is tested every day. Consider the Lorentz transformation, the equation that translates coordinates from one observer's frame to another. If you and I are moving relative to each other, and we both measure the same two events, we will disagree about the time interval between them. The transformation tells us exactly how much we disagree. One part of the equation, the term v times x divided by c squared, mixes your position in space with your position in time. Move toward an event, and your now shifts forward. Move away, and it shifts backward. The shift is small at ordinary speeds, but it grows with distance. At the scale of a galaxy, a slow walk becomes a multi-day discrepancy. In 1989, physicist Roger Penrose illustrated this with a thought experiment now called the Andromeda paradox. Two people pass each other on a sidewalk, walking in opposite directions at about 1 meter per second, a casual stroll. The Andromeda galaxy is 2.5 million light-years away. According to special relativity, the two pedestrians' planes of simultaneity, the set of events each one considers to be happening now, are tilted relative to each other because they are moving. The tilt is tiny, but the distance to Andromeda amplifies it. By the time the tilt reaches Andromeda, the two people's nows are separated by roughly 3 days. If they are walking in opposite directions, the gap doubles to about 6 days. That means one person's now might include an Andromedan space fleet that has already launched, while the other person's now includes a decision that has not yet been made. Not a decision they think has not been made. A decision that, according to the geometry of spacetime as sliced from their reference frame, genuinely lies in the future. Yet both observers are standing on the same sidewalk, a few meters apart, in the same moment. How is that possible? The answer is that simultaneity, the idea of at the same time, is not a fact about the universe. It is a fact about the observer. Events that are separated in space do not have an invariant time order unless they are connected by a causal chain. If light from one event can reach the other, the order is fixed. Cause comes before effect, and every observer agrees. But if the events are too far apart for light to connect them, they are space-like separated, and before and after lose their meaning. They become frame-dependent labels, as arbitrary as calling one direction north. This is not a defect in relativity, it is a feature, and it is confirmed at every scale we can measure. In 2010, physicists at the National Institute of Standards and Technology in Boulder, Colorado, placed two aluminum-ion optical clocks 33 centimeters apart, about 1 foot, the height of a typical stair-step. They measured the gravitational time dilation difference between the two clocks and found a fractional frequency shift of 4.1 plus or minus 1.6 times 10 to the negative 17th power. That is a real, measurable difference in the rate at which time passes. Your head, sitting 1 foot higher than your feet, experiences time slightly faster. Over a 79-year lifetime, your head ages roughly 90 billionths of a second more than your feet. The effect is far too small for a human to perceive, but it is not too small to measure, and it confirms what the equations predict. Time is not a universal river flowing at the same rate everywhere. It is a local phenomenon, a property of paths through spacetime, and it depends on where you are and how you move. 2 years later, in 2022, a team at JILA in Boulder pushed the measurement even further. They used a lattice of ultra-cold strontium-87 atoms and resolved gravitational redshift across a distance of 1 millimeter, about the width of a pencil tip. The fractional frequency uncertainty was 7.6 times 10 to the negative 21st power. A millimeter. You can hold two clocks a millimeter apart, and they will tick at measurably different rates. What does that mean for punctuality? It means the idea of a single universal clock counting down to 3 p.m. is an approximation that works only because we move slowly and stay close together. If you and I synchronize our watches at 2:50, and then you climb a flight of stairs while I stay on the ground floor, our watches will drift. Not much, billionths of a second, but they will drift, and the drift is not an error in the clocks. It is a fact about space-time. By the time you walk into the meeting room, your watch and the clock on the wall will have followed different paths through space-time and accumulated different amounts of proper time. The question, "Did you arrive at 3 o'clock?" has no single answer. It depends on whose clock you ask. And if you ask the universe as a whole, the universe gives no clock at all. In the 1960s, physicists John Wheeler and Bryce DeWitt attempted to merge quantum mechanics with general relativity by quantizing Einstein's field equations. The result was the Wheeler-DeWitt equation, and it contains a shock. The equation reads, "The Hamiltonian operator acting on the wave function of the universe equals 0. The Hamiltonian is the operator that generates time evolution in quantum mechanics. If it equals 0, there is no time evolution. The wave function of the universe does not change. It does not evolve from one moment to the next. It simply is, a static mathematical object describing all possible configurations of matter and geometry at once." This is called the problem of time, and it is one of the deepest puzzles in theoretical physics. General relativity describes spacetime as a dynamical, evolving structure, but when you write down the quantum version, time disappears. The universe, seen from outside, is timeless. Physicists have proposed many ways to recover time, to show how the flow we experience emerges from a static, timeless structure, but none is universally accepted. The problem remains open. One proposal, put forward in 1983 by physicists Don Page and William Wouters, suggests that time is relational. The universe as a whole is in a stationary quantum state, a state that does not evolve. But if you condition on one subsystem, treating it as a clock, the rest of the universe appears to evolve relative to that clock. Time is correlation, not flow. An observer inside the universe, entangled with a clock, sees change. An observer outside sees a static, unchanging wave function. In 2013, a team led by physicist Ekaterina Moreva at the Istituto Nazionale di Ricerca Metrologica in Turin demonstrated this mechanism experimentally using two entangled photons. One photon played the role of a clock, the other played the role of a system. When they measured the system photon conditioned on the clock, they saw evolution. When they measured the global state, they saw a static, stationary state. The experiment was a toy model, but it showed the mechanism is consistent. A static universe can look like an evolving one from the inside. Keep that mechanism in mind. For now, the question is this: if simultaneity is observer-dependent, if time dilation is real, if the best quantum equation for the universe is timeless, then what does it mean to say the meeting starts at 3 p.m? Who's 3? Measured by which clock, along which path? The natural answer, and the one that has dominated physics since Minkowski, is that the meeting is not a moment in time. It is an event in space-time. An event is a point with 4 coordinates, 3 for space, 1 for time. But those coordinates are frame-dependent. Change your velocity and the coordinates change. What does not change is the event itself, the geometric fact that 2 worldlines intersect. Your worldline and the meeting's worldline cross at a specific point in space-time, and every observer agrees that the crossing happens. They just disagree about the coordinates. This is the invariant definition of an event, and it is the definition relativity forces on us. An event is not 3 p.m. on the clock. An event is the coincidence of two worldlines. You arrive at the meeting when your path through space-time crosses the path traced by the meeting room. That crossing is a single, unique point. It does not happen at a time, it happens at a point. And once it happens, it is part of the geometry of space-time forever. It does not become real. It is real, in the same way a point on a curve is real whether you have traced the curve yet or not. This is the core of Eternalism, and it is why Eternalism is sometimes called the block universe. If space-time is a four-dimensional structure, and all events are points in that structure, then past, present and future are not ontologically different. They are directions in space-time, like north and south. The past is the set of events in your past light cone, the region of space-time from which light could have reached you. The future is the set of events in your future light cone, the region you could influence by sending a light signal. Everything else is elsewhere, space-like separated, simultaneous in some frames and not in others. And the structure as a whole is fixed. The block does not grow or change. It is a static, timeless geometry, and you are a thread woven through it.
That is one reading. It is not the only reading, but it is the reading that follows most directly from Minkowski's geometry and the relativity of simultaneity. And it has consequences. If the block is real, then the meeting at 3 p.m. is not waiting to happen. It already exists, in the same sense that a point 50 kilometers north of here already exists, even though you have not traveled there yet. You do not bring the meeting into existence by arriving at it, you intersect it. And if the meeting already exists, then every meeting you will ever attend already exists. Your last day of work, your final conversation, the moment you take your last breath, all of it is already laid out, fixed, a thread in the block. The future is not open. It is simply the part of space-time you have not yet intersected. This is the view many physicists adopt, though not all. It is the view implied by the geometry of relativity, and it is the view Einstein himself seemed to hold near the end of his existence. On March 21, 1955, 3 weeks before his own death, Einstein wrote a letter of condolence to the family of his lifelong friend, Michael Besso, who had just died. He wrote, "Now he has departed from this strange world a little ahead of me. That signifies nothing. For those of us who believe in physics, the distinction between past, present and future is only a stubbornly persistent illusion." That sentence has been quoted countless times, and it is worth stating clearly what it is and what it is not. It is a personal letter, not a scientific statement. It was written to console a grieving family, and it reflects Einstein's own view of time, shaped by decades of thinking about relativity. But it does not settle the question. Philosopher of physics Tim Maudlin has argued that nothing in relativity itself, no experiment, no equation, establishes that the distinction between past, present, and future is an illusion. Relativity shows that simultaneity is relative. It does not show that becoming is unreal. This is a crucial distinction, and it is where the debate turns. The argument for eternalism, stripped to its core, runs like this. If simultaneity is relative, then there is no objective present. If there is no objective present, then there is no objective boundary between the past, which exists, and the future, which does not. Therefore, either nothing exists or everything exists. Eternalism is the view that everything exists. The alternative, that only the present exists and the present is different for different observers, is called presentism, and it has a problem. If the present is relative, then what exists is relative. For one observer, the Andromedan fleet has launched and exists. For another, it has not and does not. That sounds like a contradiction. One way out is to deny that there is any objective fact about existence at all.
Another way is to accept that the block is real but growing, that the past and present are fixed, but the future is genuinely open, and the block advances, adding new layers of spacetime as time passes. This view is called the growing block universe, and it was first proposed by philosopher C.D. Broad in 1923. A modern version, developed by cosmologist George Ellis and physicist Tony Rothman, is called the crystallizing block universe. In their model, quantum indeterminacy crystallizes into classical definiteness at the present, and the present itself is defined by measuring proper time along Ricci eigenlines from the start of the universe. Ellis writes, "The arrow of time arises simply because the future does not yet exist." But defining a covariant global present, a present that all observers agree on, is difficult in relativity, and many physicists argue it is impossible without introducing a preferred frame, which relativity forbids. The counter-argument is that cosmology does give us a preferred frame, the frame in which the cosmic microwave background is isotropic, the frame that defines the large-scale structure of the universe. In that frame, you can foliate spacetime into a sequence of space-like hypersurfaces and call each hypersurface a moment of cosmic time. Ellis's present is defined this way. But even if you grant the frame, the question remains: is the present a real boundary where new spacetime comes into being? Or is it just a useful coordinate slice through a static block? That question is still open, and it is not the only way to challenge eternalism. In the late 1980s, physicists Raphael Sorkin, Luca Bombelli, Johann Lee, and David Meyer proposed a radical idea. Spacetime is not continuous. It is discrete, made of fundamental units they called causal sets. A causal set is a partially ordered set of events, where the order represents causality. If event A is in the causal past of event B, then A comes before B in the set. The number of elements in a region corresponds to the region's volume. The slogan is, "Order plus number equals geometry." You can recover the entire geometric structure of spacetime, distances, angles, curvature, just by counting the elements and knowing their causal relationships. But here is the key. In the standard causal set picture, the set is static. The entire causal history of the universe is given all at once, and observers simply trace paths through it. But in 1999, physicists David Rideout and Raphael Sorkin introduced a dynamical version called classical sequential growth. In CSG, the causal set grows. New elements are born one at a time, added to the existing set according to a probability rule. The growth is random but constrained. A new element can only be born to the future of existing elements, never to their past. This is called internal temporality, and it is a way of building becoming directly into the structure of spacetime. Sorkin has argued that this growth is a genuine physical process, not just a coordinate artifact. He wrote, "One often hears that the principle of general covariance forces us to abandon becoming. To this claim, the CSG dynamics provides a counterexample. The birth of each new spacetime atom is the happening of an event. Once born, the element signifies that the event has already happened. Time in this picture is not an illusion. It is the growth of the causal set." Physicist Faye Dowker, a leading advocate of causal set theory, puts it this way: "The birth of spacetime atoms as the passage of time is the picture that correlates less well with our sense experience than the one in which the birth of new spacetime atoms is a physical process. In other words, the growing causal set is a better match for what we feel, the sense that the present is real and the future is not yet." But critics, including philosopher of physics Christian Wüthrich, argue that the growth is not as physical as it seems. Wüthrich writes, "This hope is faint at best, as a block view offers the most natural interpretation of dynamical causal set theory. The worry is that CSG can be reformulated in a timeless way, with the growth reduced to a feature of the way observers embed themselves in the causal set, not a feature of the set itself. The debate is unresolved, and it is technical, but the stakes are clear. If CSG growth is real, then the block is not static. Spacetime genuinely becomes. Another challenge comes from physicist Nicholas Gisin, who argues that the deterministic block rests on a hidden assumption that real numbers are physically real. In classical mechanics, the state of a system is specified by giving the positions and velocities of all its parts. If those are real numbers, and real numbers contain infinite information, then the initial conditions determine the future with infinite precision. The block is fixed. But Gisin points out that a finite region of space cannot hold infinite information. A typical real number, he argues, is not physically relevant. The numbers that matter, the ones you can actually measure and compute with, are computable numbers or constructible numbers, and those have finite information content. In a series of papers published between 2019 and 2021, Gisin proposed replacing real numbers with intuitionistic real numbers, which are numbers that acquire digits over time as the result of a random process. In this framework, classical mechanics becomes indeterministic, even though the equations look the same. The future is genuinely open, not because quantum mechanics is random, but because the initial conditions themselves are incomplete. Time, in this picture, is creative. New information comes into being as the universe evolves. Gisin writes, "We must bring classical physics closer to quantum physics by finally incorporating indeterminacy." The framework is empirically equivalent to standard classical mechanics. It makes the same predictions, but it shifts the ontology. Instead of a fixed block with illusory becoming, you have real becoming with deterministic-looking equations. Whether this counts as physics or philosophy of mathematics is debated, but it shows that the block is not forced by the equations alone. It depends on what you take numbers to mean. Physicist Smolin has taken an even stronger position. In his 2013 book Time Reborn, Smolin argues that time is fundamental, not emergent, and that the laws of physics themselves evolve. He criticizes the block universe as a confusion between timeless mathematical models and the reality they describe. In an interview, he said, "Time is paramount, and the experience we all have of reality being in the present moment is not an illusion, but the deepest clue we have to the fundamental nature of reality." He admits the view has problems. He calls the question of what determines how laws evolve the meta-law dilemma, and he concedes it is currently a sticking point. But he defends real, irreducible time as the foundation of physics. So where does that leave punctuality? If the block is real and static, then the meeting at 3 p.m. is a fixed point in space-time. You cannot be late in any absolute sense, because there is no universal clock to which lateness is relative. You simply intersect the meeting's world line at a particular point, and every observer agrees that the intersection happens. They disagree about the coordinates, about how much time elapsed on your watch, about whether you arrived before or after someone else, but they agree on the event itself. Being late, in this picture, is a local relationship. It is the fact that your world line intersects the meeting's world line at a point where the wall clock reads 3:05 instead of 3 o'clock. That is a geometric fact, not a temporal one. It is like saying you are north of the meeting room instead of inside it. But if becoming is real, if the CSG causal set grows, or the block crystallizes, or time is fundamental as Smolin argues, then the meeting does not exist yet, not even as a fixed point you have not reached. It will come into being when the present reaches it, and whether you are late depends on whether your world line reaches that point before the clock on the wall ticks past 3 o'clock. The geometry is the same, the ontology is different. In one picture, you trace a pre-existing thread. In the other, you write the thread into being as you go. Which picture is right? That is the question, and it is time to see what the evidence shows. Start with what is firmly established. The relativity of simultaneity is not in doubt. It has been tested in particle accelerators, confirmed by muon decay rates, verified by GPS corrections, and demonstrated in every high-energy physics experiment for a century. Two observers in relative motion genuinely do assign different coordinates to space-like separated events, and there is no experiment that can single out one observer's coordinates as the objective truth. That is settled. The invariance of the spacetime interval is also settled. The quantity s squared equals negative c squared t squared plus x squared plus y squared plus z squared, or its equivalent in other signature conventions, is the same for all observers, even when they disagree about time and space separately. That invariance is the bedrock of relativity, and it has been tested to extraordinary precision. What is not settled is whether that geometry entails eternalism. The strongest argument for eternalism is the Rietvdijk-Putnam-Maxwell-Penrose argument, first stated by Dutch physicist C. Wim Rietvdijk in 1966, and independently by philosopher Hilary Putnam in 1967. The argument goes like this. If two events are simultaneous for one observer, then both events are real for that observer. If simultaneity is transitive across observers, then distant future events are as real as present events, because you can construct a chain of observers with overlapping simultaneity planes that reaches any event in spacetime. Therefore, the future is already real. But philosopher of physics Howard Stein proved, in two papers published in 1968 and 1991, that the argument fails. The problem is the transitivity assumption. Simultaneity is not transitive in Minkowski spacetime. If event A is simultaneous with event B in one frame, and event B is simultaneous with event C in another frame, it does not follow that A is simultaneous with C in any frame. More fundamentally, Stein showed that you can define an objective becoming relation in Minkowski spacetime under natural axioms, and the result is that only the events in your past light cone are definite as of any given point. The past is fixed. The future is not yet determined. Simultaneity collapses to a local, point-like present. Stein's result is widely regarded as the strongest technical rebuttal to the eternalist reading of relativity. It does not prove presentism. It proves that a coherent, objective notion of becoming is compatible with relativity, and that the Rietvdijk-Putnam argument does not force eternalism. What about the other evidence? The Page-Wouters mechanism and the Morava experiment show that emergent time is possible. They show that a static, timeless quantum state can look like an evolving universe from the inside, but they do not show that the actual universe is in such a state. The experiment used 2 photons in a lab. The universe is not 2 photons. Scaling up the mechanism to the real universe requires solving the problem of time, and that problem is unsolved. So the experiment is evidence for consistency, not actuality. The Wheeler-DeWitt equation is timeless, but it is also a provisional equation. It applies to situations where spacetime has no boundary and no external reference. Cosmologists use it to explore the quantum origin of the universe, but it is not a final theory. Loop quantum gravity, string theory, and other approaches to quantum gravity may restore time in different ways. The equation's timelessness does not prove the universe is timeless. It shows that we do not yet know how to reconcile quantum mechanics with general relativity in a way that preserves time as we experience it. The BGV theorem, the Borde-Guth-Vilenkin theorem, proves that any spacetime with positive average expansion, when measured backward along past-directed geodesics, is geodesically past incomplete. It has a past boundary. The theorem is widely accepted, and it tells us something significant. If the universe is expanding on average, then the past is finite. There was a first moment, or a boundary beyond which the geometry breaks down. But the theorem says nothing about whether that boundary is a static feature of the block, or the starting point of a dynamic process. It says nothing about becoming. Conformal cyclic cosmology, Roger Penrose's model of an infinite sequence of eons, gives the block a future boundary as well as a past boundary. The far future of one eon, stretched to infinite time by accelerated expansion, is conformally rescaled to become the start of the next eon. If CCC is right, the block has edges, a past edge and a future edge, but it is still a block. The edges are features of the geometry, not moments of genesis or annihilation, and CCC remains speculative. The claimed CMB Hawking points that would support prior eons are contested, and the choice of conformal factor is unresolved. The model is a serious proposal, but it is not confirmed. Causal set growth is the most direct challenge to the static block, but the challenge is internal to the theory. If CSG is genuinely covariant, if the growth is independent of how you foliate spacetime into time slices, then it is a real physical process, and the block grows. But if the growth can be reformulated as a gauge choice or a perspectival artifact, then it is not as physical as it looks. The debate turns on technical details, and it is ongoing. What is clear is that the theory exists, it is consistent with relativity, and it shows that becoming is not ruled out by the causal structure of spacetime. So what does the evidence actually show? The evidence shows that there is no universal present. The idea that everyone shares a single cosmic now, ticking forward in lockstep, is incompatible with relativity. Presentism, in its naive form, the view that only the present exists and the present is the same for everyone, is refuted. The evidence also shows that the causal structure of spacetime is invariant. Every observer agrees on which events are in the past light cone, which are in the future light cone, and which are space-like separated. The structure of before and after for causally connected events is not relative, it is fixed. What the evidence does not show is that the block is static. The geometry is fixed. The ontology, whether the future is real or whether it comes into being, is not determined by the geometry alone. Eternalism is the simplest interpretation, the one that treats spacetime as a completed structure and avoids the complications of defining a moving present. But simplicity is not proof. Stein's result, CSG dynamics, Ellis's crystallizing block, Gisin's intuitionist indeterminism, and Smolin's fundamental time all show that real becoming is compatible with the same geometry. The equations do not choose, they are neutral.
And that brings us to the original question. Can you be late? If eternalism is right, then no, not in any absolute sense. The meeting is a fixed point in spacetime. You are a world line intersecting that point. Late is a description of the coordinates of the intersection, not a fact about temporal priority. You do not arrive after the meeting starts. You arrive at a point whose time coordinate, measured by the wall clock, reads 3:05 instead of 3 o'clock. That is a geometric fact, as objective as the distance between 2 points on a map, but it is not a fact about becoming. The future meeting does not come into being when you arrive. It was already part of the block. If becoming is real, if the causal set grows, or the block crystallizes, or time is fundamental, then yes, you can be late, because the meeting does not exist until the present reaches it. Your world line and the meeting's world line are both growing, extending forward as new spacetime comes into being, and whether you are late depends on which world line reaches 3 o'clock first. The geometry is the same. The meeting is still a world line intersection, but the intersection does not pre-exist your arrival. It happens when you arrive, and before that, it is genuinely open. Which is true. Physics cannot settle that question, not yet. The evidence shows the geometry. It shows that simultaneity is relative, that causal order is invariant, that time dilation is real, and that there is no universal clock. But it does not show whether the geometry is all there is, or whether the geometry is the shape left behind by a process of becoming. That question is open. It is one of the deepest open questions in the foundations of physics, and it reaches down to the boundary between science and metaphysics. Here is what is honest. The relativity of simultaneity rules out the everyday picture of lateness, the picture in which the meeting sits in an open future, waiting to happen, and you race through a universal flow of time to reach it. That picture is incompatible with special relativity. But the relativity of simultaneity does not rule out becoming. It rules out a global, observer-independent now. It does not rule out a local, causally structured becoming, where the past is fixed and the future comes into being at the forward edge of the present. That remains possible. The best current interpretation, the one most physicists adopt,
the one that fits most naturally with the geometry of Minkowski spacetime, is Eternalism, the block universe. Past, present and future as equally real, with temporal passage as a perspectival feature of observers embedded in the block. But that interpretation is not forced, it is chosen. And the choice matters, because it shapes how we understand ourselves. If the block is static, then every decision you will make is already made. Not in the sense that you have no choice. The decision is yours, and it is real, and it is part of the block. But in the sense that the decision, once made, is fixed forever. It does not become real when you make it. It is real from the perspective of the whole, outside time. Your existence is not a sequence of moments flowing from an open past toward an uncertain future. It is a single thread, complete and unchanging, traced through space-time. The question of whether you can be late turns on the question of whether the future is real, and that question reaches deeper than relativity alone can answer. There is a structure beneath the geometry, a structure built from causality itself, and it is worth understanding how deep it goes. In the 1950s, mathematician A.D. Alexandrov, working with V.V. Ovchinnikova, proved a theorem about spacetime that most physics students never encounter, but it is foundational. The theorem says that if you know only the causal order of events, which events can influence which other events, without any measurements of distance or time, you can reconstruct the entire topology of spacetime. You can tell which regions are connected, which are separate, and how the structure fits together. The causal order alone determines the shape. This was rediscovered independently by mathematician E.C. Zeeman in 1964 and extended into what is now called the Alexandrov-Zeeman theorem. Zeeman proved that any bijection of Minkowski space that preserves the causal order, any map that sends light cones to light cones, must be a combination of a Lorentz transformation, a translation, and a dilation. In other words, causality determines the metric up to a single global scale factor. If you know what can cause what, you know almost everything about spacetime. You know the geometry, you know the distances, you know the angles. The only thing you do not know is the overall size. What does that mean for punctuality? It means that before and after for causally connected events are not just labels, they are the structure. The meeting can cause you to remember it afterward. Your arrival can cause the meeting to begin. Those causal relationships are invariant. Every observer agrees on them. And those relationships alone, the fact that one event is in the causal future of another, are enough to reconstruct the geometry. Being late is not a fact about flowing time. It is a fact about causal structure. Your world line intersects the meeting's world line at a point where the meeting has already started, and that already is a statement about light cones, not about a universal clock. This is the deepest sense in which punctuality is geometric. It is not about arriving before a moment happens. It is about arriving at a point in spacetime where the causal structure places you after the event you were supposed to reach before. And that structure is invariant. It is the skeleton of spacetime itself. But if the skeleton is fixed, does that mean the future is fixed as well? Not necessarily. The causal structure tells you which events can influence which other events. It does not tell you whether those events are already real, waiting to be reached, or whether they come into being as the present advances. The geometry is neutral on that question, and that is where the competing interpretations diverge. Consider the evolving block universe, the model proposed by George Ellis and Tony Rothman in 2010. They argue that spacetime does not exist all at once. It grows. The past and present are real, but the future is not. The present is the forward boundary of the block, and it advances, adding new layers of spacetime as time passes. Ellis defines the present by measuring proper time along Ricci eigenlines, the world lines of free-falling observers who follow the curvature of spacetime without any external forces. From the initial emergence to now, you measure how much time has passed on those world lines, and that defines a global now. Every observer who has aged the same amount since the initial emergence is in the same present. The idea is that quantum indeterminacy resolves into classical definiteness at the present. Before the present, the past is fixed. After the present, the future is genuinely open. Ellis calls this the crystallizing block universe, because the structure crystallizes as it grows, turning quantum possibilities into classical facts. He writes, "The arrow of time arises simply because the future does not yet exist." The model has appeal. It matches our intuition that the past is settled and the future is open. It explains the arrow of time without requiring a special initial condition or an external flow. And it is compatible with general relativity, as long as you accept that the Ricci eigenlines define a preferred foliation, a preferred way of slicing spacetime into moments. But the model also has a problem. Defining a global present in a relativistic spacetime is difficult. In special relativity, there is no preferred frame, so there is no natural way to pick out a single foliation. In cosmology, the cosmic microwave background gives you a frame, the frame in which the CMB is isotropic, and that frame is often used to define cosmic time. But that frame is defined by matter, not by spacetime itself. It is a feature of the particular distribution of energy in our universe, not a fundamental property of geometry. And if the present is defined by a matter distribution, then it is contingent, not necessary. A different universe might not have a preferred frame at all. Stein's rebuttal to the Reet-Dyck-Putnam argument makes a related point. Stein showed that you can define an objective becoming relation in Minkowski spacetime, but the result is not a global present. It is a local present, confined to the past light cone. For any point in spacetime, the events in its causal past are definite as of that point. Everything else, the space-like separated events and the future events, is not yet definite. The present collapses to a point, and becoming is real only in the sense that the past grows as you move forward along a world line. This is a minimal form of becoming. It preserves the idea that the future is open, but it makes the present local, not global. Two observers at the same point in space but moving at different velocities will have different causal pasts, so they will disagree about which events are definite. The present, in Stein's picture, is not a hypersurface that slices through spacetime. It is a light cone, attached to each observer, moving forward as the observer moves. That picture is compatible with relativity, but it is also strange. It means that the future is open for you, but not for the universe. There is no moment when the universe as a whole transitions from future to present. There are only local moments, one for each observer, and those moments do not line up. Does that preserve becoming in any meaningful sense? Philosophers disagree. Some say yes, because it keeps the distinction between the definite past and the open future. Others say no, because it makes becoming relative to each observer, which is almost as strange as saying the future is already real. The causal set approach takes a different path. Instead of trying to define a present within a continuous spacetime, it replaces spacetime with a discrete structure from the start. A causal set is a collection of events with a partial order. Some events come before others, some come after, and some are incomparable. The order represents causality. If event A causes event B, then A comes before B in the set. The number of events in a region represents the volume of that region. No coordinates, no continuum, no foliation, just order and number. In the standard causal set picture, the set is given all at once, and the history of the universe is the entire set. But in classical sequential growth, developed by David Rideout and Raphael Sorkin, the set grows. New elements are added one at a time, born into the existing structure according to a probability rule. Each new element can only be born to the future of existing elements, never to their past. The rule is stochastic, but constrained by causality. The growth preserves the causal order.
Sorkin argues that this growth is a real physical process, and that it provides a counterexample to the claim that general covariance, the principle that the laws of physics are the same in all coordinate systems, rules out becoming. He writes,
One often hears that the principle of general covariance forces us to abandon becoming. To this claim, the CSG dynamics provides a counterexample. The growth is random, but it is not arbitrary. The probability of a new element being born depends on the volume of the region it is born into, measured by counting the existing elements. If you sprinkle elements randomly into a continuous spacetime according to a Poisson distribution, you recover the expected geometry on average. The discreteness is at the Planck scale, far below anything we can measure, so the theory reproduces general relativity in the continuum limit. But at the fundamental level, spacetime is made of atoms, and those atoms come into being one at a time. This is genuine becoming, if it is real. The causal set does not exist all at once. It grows, and the growth is irreversible. Once an element is born, it is part of the set forever. The past is fixed, but the future is not yet born. The meeting at 3 p.m. does not exist until the causal set grows enough elements to include it. Before that, it is genuinely not real. But critics point out that the growth can be reinterpreted. If you imagine an external observer outside time, looking at the entire history of the causal set, that observer sees a static structure. The growth is an artifact of being inside the set, tracing a path through it. From the outside, the set is a completed whole, with the growth simply describing the order in which elements appear along a particular world line. This is analogous to the way a movie is a static reel of film, but a viewer inside the movie experiences it as unfolding. The question is whether the growth is fundamental or perspectival. Faye Dowker, one of the leading researchers in causal set theory, argues that the growth is fundamental. She says the birth of spacetime atoms is the passage of time, and the block universe picture is the one that fits less well with our experience. But Christian Wüttrich, a philosopher of physics who has studied causal sets in detail, is skeptical. He writes, "This hope is faint at best, as a block view offers the most natural interpretation of dynamical causal set theory. The growth, he argues, may be a gauge choice, not a physical process. The debate is technical, and it has not been settled. But it shows that the question of becoming is still open, even within the framework of relativistic causality. The geometry does not force an answer. Nicholas Gisin's intuitionist approach offers yet another path. Gisin is a physicist at the University of Geneva, known for his work on quantum foundations and quantum cryptography. In a series of papers published between 2019 and 2021, he argued that the deterministic block universe rests on an assumption physicists rarely question, that the state of a physical system can be specified by real numbers, and that real numbers contain infinite information. In classical mechanics, you describe a particle by giving its position and velocity. If those are real numbers, and you know them with infinite precision, then the laws of motion determine the particle's entire future trajectory. The block is fixed. But Gisin points out that a finite region of space, any region smaller than the observable universe, cannot contain infinite information. A typical real number, chosen at random, has infinitely many digits, and no finite physical system can store them all. So typical real numbers, he argues, are not physically relevant. They are mathematical idealizations.
The numbers that matter are the ones you can actually measure and compute. Rational numbers, algebraic numbers, computable numbers. Those numbers have finite information content, and if the initial conditions of a system are specified by such numbers, then the future is not determined with infinite precision. Small uncertainties grow over time, and the system becomes unpredictable. Classical mechanics, in this picture, is not deterministic. It only looks deterministic if you assume infinite precision, which is unphysical. Gisin goes further.
He proposes replacing real numbers with intuitionistic real numbers, a concept from mathematical logic. An intuitionistic real number is one that is constructed by an algorithm, and the algorithm may be non-terminating. The digits of the number are revealed over time as the algorithm runs, and they may depend on random choices made during the construction. In other words, the number does not exist all at once. It comes into being as time passes. And if the state of the universe is described by such numbers, then the future is genuinely open. New information comes into being as time flows, not because the laws are stochastic, but because the numbers themselves are incomplete. Gisin calls this creative time. He distinguishes between geometric time, which is the parameter that appears in the equations of physics, and creative time, which is the process by which new information is generated. Geometric time is reversible and deterministic. Creative time is irreversible and indeterministic. The two are compatible, he argues, because geometric time is a description of patterns in a timeless mathematical structure, while creative time is the reality beneath it. The framework is empirically equivalent to standard classical mechanics. It makes the same predictions for any measurement you can actually perform, because measurements have finite precision. But it shifts the ontology. Instead of a fixed block with illusory becoming, you have real becoming with deterministic-looking equations. Gisin writes, "We must bring classical physics closer to quantum physics by finally incorporating indeterminacy." The idea is controversial. Some physicists see it as a genuine contribution to the foundations of physics. Others see it as a reinterpretation that changes nothing about the practice of science. But it shows, once again, that the block is not forced by the equations. It depends on what you take the equations to mean. Smolin has argued for an even more radical view, that time is fundamental, not emergent, and that the laws of physics themselves evolve. In his book, Time Reborn, published in 2013, Smolin criticizes the block universe as a mistake born from confusing mathematical models with reality. Physicists, he argues, have been seduced by the elegance of timeless mathematics and have forgotten that time is the one thing we experience directly. The flow of time, the openness of the future, the irreversibility of the past. These are not illusions. They are the deepest facts about the universe. Smolin's view is a minority position, but it is not a fringe position. He is a respected physicist at the Perimeter Institute, and his work on loop quantum gravity and cosmology is taken seriously. His argument for fundamental time rests on several pillars. First, he argues that cosmology requires a global time. The universe as a whole is not stationary. It expands, it evolves, and that evolution is real, not perspectival. Second, he argues that the laws of physics may themselves evolve. If the laws were fixed from the beginning, then they are unexplained, a brute fact. But if the laws evolve, then they can be selected by cosmological processes, and the universe can explain its own regularities. Smolin calls this cosmological natural selection, and he has proposed testable predictions, though the tests are difficult and the results so far are inconclusive. Third, he argues that the timeless models physicists use, the Wheeler-DeWitt equation, the path integral formulation of quantum mechanics, the block universe of relativity, are approximations. They work within certain regimes, but they break down when you ask about the universe as a whole or the origin of the laws. The approximations are useful, but they are not the deep truth. Time, he argues, is more fundamental than space, more fundamental than the laws, more fundamental than mathematics. It is the background against which everything else unfolds. Smolin's view has been criticized on several fronts. Some critics argue that evolving laws face a meta-law dilemma. If the laws evolve, what determines how they evolve? You need a meta-law, and then a meta-meta-law, and so on, leading to an infinite regress. Smolin acknowledges this as currently a sticking point, but he believes it can be resolved by finding principles that are so general they do not require further explanation. Other critics argue that cosmological natural selection makes predictions that are either already ruled out or untestable, and that the whole framework is speculative. But whether Smolin is right or wrong, His work demonstrates that fundamental time is a live option. It is not ruled out by relativity, by quantum mechanics, or by the success of timeless models in limited domains. It is a scientific hypothesis, with proposed mechanisms and potential tests, and it keeps the door open to real becoming. So the question remains, if you are late to the meeting, is the meeting already real, waiting for you in the block, or does it come into being when the present reaches it? The geometry says nothing about that question. The causal structure is fixed, the invariant interval is fixed, the light cones are fixed. But whether those structures are features of a static block, or the shape left behind by a growing process, is not determined by the geometry alone. You need additional assumptions about the nature of reality, the meaning of existence, the relationship between mathematics and physics, to close the gap. And that is where the evidence reaches its limit. Physics can tell you that there is no universal present. It can tell you that simultaneity is relative, that time dilation is real, that causal order is invariant. It can tell you that the Wheeler-DeWitt equation is timeless, that the Page-Wouters mechanism works in principle, that the BGV theorem proves a past boundary, that causal sets can grow or be static, depending on how you interpret the dynamics. But it cannot tell you whether the future is real. That is an open question, and it is likely to remain open until we have a complete theory of quantum gravity and a clear understanding of how time emerges, or does not emerge, from the fundamental structure of the universe. We are not there yet.
In the meantime, there are concrete consequences. If the block is static, then every event is equally real, and the distinction between past, present, and future is perspectival. Your existence is not a sequence of moments, one replacing the next. It is a single, unchanging structure, a world line traced through space-time, and the flow of time is a feature of your experience, not a feature of the structure itself. You cannot be late in any absolute sense, because the meeting does not wait for you. It is simply a point in space-time, and your arrival is another point, and the relationship between them is geometric. But if becoming is real, then the future does not yet exist. The meeting is not waiting. It will come into being when the present reaches it, and until then, it is genuinely open. You can be late, because the meeting has a temporal priority that is not reducible to geometry. It happens first, and you arrive after, and that after is a fact about the order in which events come into existence, not just a fact about coordinates. Which picture you adopt shapes how you think about yourself. If the block is static, then your decisions are part of the structure, fixed and unchangeable from the perspective of the whole. You make choices, and those choices are real, but they are not open in the sense of being undetermined. They are part of the thread you trace through space-time, and from the outside, the thread is complete. If becoming is real, then your decisions are genuinely open. The future is not yet written, and each choice you make adds something new to the universe, something that was not there before. The question of punctuality, then, is not just about meetings and clocks. It is about the nature of time, the reality of the future, and the structure of existence itself. And it is a question that physics alone cannot answer. But there is more to the story. The block universe, if it is real, does not float in a void. It has boundaries. The Borde-Guth-Vilenkin theorem, published in 2003, proved that any spacetime with positive average expansion, measured backward along past directed geodesics, must be geodesically incomplete. It must have a past boundary. The proof is kinematic. It does not depend on any assumptions about the matter or energy in the universe, only on the fact that the universe is expanding on average, and the expansion is a fact. We measure it in the redshift of distant galaxies, in the cosmic microwave background, in the large-scale structure of the universe. The theorem applies. Arvind Borde, Alan Guth, and Alexander Vilenkin, the three physicists who proved the theorem, are careful about what it means. In their paper, they write, Our argument shows that null and time-like geodesics are, in general, past incomplete in inflationary models, whether or not energy conditions hold, provided only that the averaged expansion condition holds along these past-directed geodesics. The boundary is a mathematical fact, but its physical interpretation is open. It could be a singularity. It could be a transition to a different phase of spacetime, where the classical description breaks down and quantum effects dominate. It could be a boundary where new physics takes over. Vilenkin himself interprets the theorem as evidence for a cosmic beginning. In his book, Many Worlds in One, published in 2006, he writes, "With the proof now in place, cosmologists can no longer hide behind the possibility of a past eternal universe. There is no escape. They have to face the problem of a cosmic beginning." That is a strong statement, and it reflects Vilenkin's view that the boundary is a true beginning, not just a place where the equations fail.
But other physicists are more cautious. Board, Guth and Vilenkin note in their paper that some new physics is necessary in order to determine the correct conditions at the boundary. The theorem proves incompleteness, not genesis. It says the geodesics do not extend to infinite past-affine parameter, but it does not say what happens at the boundary. That is a question for quantum gravity, and quantum gravity is not yet a finished theory. There are also potential loopholes. The theorem assumes the averaged expansion condition holds. The Hubble parameter, when averaged backward along a geodesic, is positive. But if the universe contracts for part of its history, or if it undergoes a bounce from a previous phase, the condition might not hold. Cyclic cosmologies, in which the universe goes through repeated cycles of expansion and contraction, can evade the theorem by violating the averaged expansion condition during the contracting phase. The matter content required for such a bounce is exotic. It typically requires negative energy densities or violations of energy conditions, but it is not ruled out by observation. So the BGV theorem tells us the block, if it is real, has a past edge. But it does not tell us what that edge is, or whether it is the beginning of time, or a boundary where classical geometry ceases to apply. That question is unresolved. Roger Penrose has proposed a model in which the block has both a past edge and a future edge. The model is called conformal cyclic cosmology, and it was introduced in his 2010 book, Cycles of Time. Penrose argues that the far future of the universe, when all the matter has decayed or fallen into black holes, and the black holes have evaporated via Hawking radiation, is a state of pure radiation expanding forever. In that state, the effective rest mass of everything is zero. And if the rest mass is zero, then there is no natural scale for distance or time. You can rescale the metric by a conformal factor, a smooth function that changes lengths and times by the same factor everywhere, and the physics looks the same. Penrose proposes that this future state, stretched to infinite time, is conformally equivalent to the initial emergence of a new eon. The future conformal boundary of one eon becomes the past conformal boundary of the next. Time does not end. It transitions smoothly into a new cycle, with new matter, new galaxies, new structures, but the same fundamental laws. The cosmological constant of one eon becomes the effective curvature of the next. The cycles repeat forever, each one beginning and ending with an infinite expansion. The model is ingenious, but it is also speculative. It requires the cosmological constant to be positive, which observation supports. It requires all matter to decay or lose its rest mass in the far future, which is uncertain. And it predicts observable signatures in the cosmic microwave background, circular patterns called Hawking points, where black holes from the previous eon left imprints in the CMB of this eon. Penrose and his collaborator Vahe Gurzadian claim to have found such signals in the CMB data, but the claim is controversial. Most cosmologists who have analysed the data do not see the signals, and the Planck collaboration, which operates the highest precision CMB satellite, has not confirmed them.
There is also a technical problem. To make the conformal rescaling work, you need to choose a conformal factor, a function that tells you how much to stretch the metric at each point. But the choice is not unique, and different choices give different physics. Proposals by Ezra Newman, Paul Todd, and Pavel Nurovsky disagree with each other and with Penrose's original proposal, and no consensus has emerged on which choice, if any, is correct. The problem is deep enough that a 2023 paper titled "Toward Fixing a Framework for Conformal Cyclic Cosmology" concludes that the framework is not yet well defined. So CCC is a serious proposal, but it is not confirmed. It gives the block both a past edge and a future edge, but the edges are conformal boundaries, not moments of genesis or annihilation. They are places where the geometry transitions from one eon to the next, preserving continuity across infinite time. If CCC is right, the block is a slice of an eternal multiverse of eons, each one a separate spacetime connected to the next by a conformal boundary. But even if CCC is wrong, the BGV theorem stands. The block, if it is real, has a past boundary, and that boundary is a fact the block must contain, not explain. It is a brute feature of the geometry, as unexplained as the constants of nature or the initial conditions of the universe. The problem is even starker for the static block interpretation. If the block is static, then it does not come into being. It simply is, a timeless structure, and the question, why does it exist, has no temporal answer. You cannot say the block arose, because arising is a temporal process, and the block is outside time. You can only say the block is a brute fact, a necessary existent, or you can point to something outside the block that grounds it. But whatever grounds the block cannot itself be part of the block, because the block is everything that exists in spacetime. This is the cosmological argument applied to the block universe, and it is a question the physics alone cannot settle. Physics tells you what the block contains and how its parts relate. It does not tell you why there is a block at all. That is not a failure of physics. It is a recognition that the question, why is there something rather than nothing, is not a question about mechanisms or laws. It is a question about existence itself, and it lies at the boundary between science and metaphysics. But there is one more wrinkle, and it brings us back to the problem of time. Quantum mechanics describes how systems evolve. You start with a wave function at time t equals 0, you apply the Schrödinger equation, and you get the wave function at time t equals 1 second, 1 hour, 1 year. The equation is time-dependent. It tells you how the state changes as time passes. But when you try to apply quantum mechanics to the universe as a whole, time disappears. The reason is that general relativity treats time as part of the geometry. There is no external clock ticking away in the background. Time is a coordinate, and it is dynamical. It bends, stretches, and curves along with space. When you quantize general relativity using the canonical approach, the approach that tries to write down a wave function for spacetime itself, you get a constraint called the Hamiltonian constraint. The Hamiltonian is the operator that generates time evolution in quantum mechanics. But in quantum gravity, the Hamiltonian constraint says the Hamiltonian equals 0. That means there is no time evolution. The wave function of the universe does not change. It is static. This is the problem of time, and it has been a central puzzle in quantum gravity since the 1960s. John Wheeler and Bryce DeWitt derived the constraint from first principles, and it has appeared in every canonical approach to quantum gravity since. The equation is often written as h hat acting on the wave function psi equals 0. It means the total energy of the universe is 0, and it means the wave function does not evolve. How do you reconcile that with the time we experience? One answer is that time is emergent. The wave function of the universe is static, but observers inside the universe are entangled with clocks, and when you condition on the state of the clock, the rest of the universe appears to evolve. This is the Page-Wouters mechanism,
the global state stays static, while an observer entangled with a clock sees the rest of the universe evolve relative to it. Time is correlation, not flow. Another answer is that time is an approximation that breaks down at the quantum gravity scale. In the psi-minimal limit, when spacetime is nearly classical and quantum effects are small, you can recover an approximate notion of time using the WKB method. The wave function has an oscillating phase, and the oscillations define a time variable. But the time is approximate, not fundamental. A third answer is that the constraint is a gauge condition, not a physical restriction. In general relativity, the Hamiltonian generates transformations that move you from one foliation of spacetime to another. Those transformations are gauge transformations. They change your description of the system without changing the physical state. The constraint says that physical states are invariant under such transformations, but that does not mean nothing happens. It means that evolution is relational, defined by correlations between different parts of spacetime, not by an external time. All three answers have been explored in the literature, and none is universally accepted. The problem of time is still a problem, and it matters for the question of the block, because if time is emergent, then the static wave function is the deep reality, and the block is its geometric shadow. But if time is fundamental, then the Wheeler-DeWitt equation is an artifact of the approximation, and the deep reality is a dynamical process that the equation fails to capture. Carlo Rovelli, one of the founders of loop quantum gravity, has argued that the solution is to abandon the idea of a global time altogether. In his framework, called thermal time, time is defined by the statistical properties of macroscopic systems. A system in equilibrium has no preferred time direction, but a system out of equilibrium, a system with correlations, with gradients, with asymmetries, defines a time direction through the second law of thermodynamics. Time, in this view, is not a coordinate. It is a statistical measure of irreversibility, and it is observer-dependent, defined by how you coarse-grain the system. Rovelli's slogan is, "Forget time." The deep structure of the universe is timeless, a network of quantum events connected by causal relations, and time is a high-level feature that emerges when you blur the details. The block universe in this picture is not a static spacetime. It is a timeless network, and spacetime itself is emergent, a classical approximation that breaks down at small scales.
Julian Barbour has taken a similar but more radical position. In his model, called Platonia, the universe is not a spacetime at all. It is a timeless landscape of possible configurations, a space of shapes, and the history of the universe is a path through that landscape. Each point in Platonia is a three-dimensional configuration of matter, a snapshot of the universe at an instant, with all the particles in specific positions. The landscape contains all possible configurations, and the path the universe follows is determined by a variational principle, analogous to the principle of least action. But there is no time parameter. The path is a sequence, and the sequence is ordered by similarity, not by a clock. Time, Barbour argues, is an illusion generated by records, what he calls time capsules, embedded in each configuration. You perceive time flowing because each configuration contains memories of earlier configurations, but the flow is not real. The configurations simply are, arranged in a pattern, and the pattern is Platonia. Barbour's picture is beautiful and mathematically rigorous, but it is also deeply counterintuitive. It denies that time is fundamental, and it denies that change is real. The universe does not evolve. It is a static structure, and motion, duration, and history are all emergent features of the way observers embed themselves in the structure. The block universe in Barbour's hands becomes even more static than it is in relativity. It becomes timeless. But not everyone agrees. Lee Smolin has argued that Barbour's Platonia, like the Wheeler-DeWitt equation and the block universe, is a mathematical model mistaken for reality. Smolin says time is real,
not emergent, and that the experience of the present moment is the deepest clue we have to the nature of the universe. The timeless models, he argues, are useful tools, but they are not the final story. They are approximations that work in certain regimes, and they break down when you ask about the universe as a whole. The debate between Rovelli, Barber, and Smolin is one of the most fundamental in theoretical physics, and it is unresolved. It is not a debate about experiments or observations. It is a debate about what the mathematics means, about how to interpret the equations, about what counts as real. And that brings us back to the meeting. If time is emergent, if the Wheeler-DeWitt equation is the deep truth, if the Page-Wouters mechanism, or Rovelli's thermal time, or Barber's Platonia is correct, then the meeting is not an event in time. It is a configuration in a timeless structure, and your arrival is another configuration, and the relationship between them is one of correlation, not temporal succession. You cannot be late in any fundamental sense, because there is no fundamental time. There is only the pattern, the structure, the geometry, and the correlations that define what we call before and after. But if time is fundamental, if Smolin is right, if the block is a mathematical shadow of a deeper dynamical process, then the meeting does happen in time, and the future is genuinely open, and you can be late because the meeting comes into being before you arrive. The evidence does not choose between these pictures. The experiments confirm the geometry. They confirm time dilation, the relativity of simultaneity, the invariance of causal order. They confirm that there is no universal clock, no global present, no preferred foliation in special relativity. But they do not confirm that time is emergent or that the block is static. Those are interpretations, layered on top of the geometry, and the layering requires assumptions that go beyond the data.
So here is what is honest, the everyday picture of punctuality, the picture in which you race through a universal flow of time toward a meeting that has not yet happened, is incompatible with relativity. That picture is ruled out. But the question of whether the meeting is a fixed point in a static block, or a future event that comes into being when the present reaches it, is not ruled out either way. Both are compatible with the geometry. Both are compatible with the experiments. The choice between them depends on what you think the geometry means, and that is a question physics alone cannot settle. What physics can tell you is this: the structure of spacetime is causal. It is built from the relationships between events, from the fact that some events can cause others and some cannot. Those relationships are invariant. They do not depend on your frame or your velocity or your position. And those relationships alone determine the topology and almost determine the metric. The causal order is the skeleton of spacetime. If you are late to the meeting, that is a fact about causal order. Your world line intersects the meeting's world line at a point where the meeting has already started, as measured by any clock you bring with you. That is a geometric fact, as objective as the distance between 2 points on a map. Every observer agrees on it, even though they assign different coordinates to the points. The lateness is not a fact about flowing time. It is a fact about world lines, about the geometry of spacetime itself, about the invariant structure that every measurement confirms. That structure has been tested in ways that go far beyond thought experiments and equations on paper. In 1977, a team at CERN led by physicist J. Bailey placed muons, unstable particles that decay in roughly 2 microseconds when at rest, into a storage ring and accelerated them to 99.94% of the speed of light. At that velocity, the muons' internal clocks ran slower by a factor of 29. They lived 29 times longer than stationary muons, circling the ring for distances that would be impossible without time dilation. The experiment did not just confirm that time dilation is real, it confirmed that proper time,
the time measured along a world line, is path-dependent, frame-dependent, and geometric. The muons did not experience time flowing more slowly. They traced a different path through space-time, and the length of that path, measured in proper time, was different. This is not an exotic effect confined to particle accelerators. It is built into every GPS satellite orbiting Earth. Each satellite carries an atomic clock, and those clocks tick faster than clocks on the ground because they are higher in Earth's gravitational field and because they are moving at orbital velocity. The combined effect of gravitational redshift and velocity time dilation means the satellite clocks gain roughly 38 microseconds per day relative to ground clocks. If the system did not correct for that drift, GPS positions would accumulate errors of several kilometers within a single day. The correction is not a theoretical nicety, it is a practical necessity. The geometry of space-time is not an abstraction, it is infrastructure.
And the geometry reaches into the everyday. Consider a train station. Two clocks hang on opposite walls, 50 meters apart. They are synchronized to show the same time. You stand on the platform, motionless relative to the clocks, and you see them ticking in unison. Then a train passes through the station at high speed, say, half the speed of light, far faster than any real train, but slow enough to keep the numbers simple. An observer on the train looks out the window and sees the two clocks. According to special relativity, the observer on the train does not see the clocks synchronized. One clock is ahead of the other by a measurable amount, determined by the Lorentz transformation. The offset is small at ordinary speeds, but it grows with velocity and distance. At half the speed of light and 50 meters apart, the clocks differ by roughly 83 nanoseconds in the moving frame. That is not a mistake, that is the geometry. The two clocks are simultaneous in the platform frame, but not in the train frame. And there is no experiment that can determine which frame is right, because both are. Simultaneity is not a fact about the clocks, it is a fact about the frame. And if simultaneity is frame-dependent, then so is the answer to the question, what time is it right now in the meeting room 3 blocks away? The answer depends on your velocity. Walk toward the meeting, and your now shifts forward in the direction of motion. Walk away, and it shifts backward. The shift is tiny, billionths of a second for ordinary walking speeds and distances measured in city blocks. But it is real, and it accumulates over distance. If the meeting room were not 3 blocks away but 3 light-years away, the shift would be days. If it were in another galaxy, the shift would be millennia. And if two observers pass each other at ordinary speeds, their nows, at galactic distances, can differ by enough time for entire civilizations to rise and fall in one observer's present, while remaining in the other observer's future. This is not science fiction. This is the geometry of Minkowski spacetime, confirmed in every test of special relativity for more than a century. It is the reason physicists say there is no universal now, no cosmic present that everyone shares. And it is the reason the block universe is the natural interpretation of relativity, even if it is not the only interpretation. But the block, if it is real, is not an inert structure. It is a causal structure, built from light cones and worldlines, and those light cones define what can influence what. Your past light cone is the set of all events that could have sent you a signal. Your future light cone is the set of all events you could influence by sending a signal. Everything outside those cones is elsewhere, space-like separated, and the order of those events is frame-dependent. But the light cones themselves are invariant. Every observer agrees on them, and that means every observer agrees on causal order. If event A causes event B, then A is in the past light cone of B in every frame. No observer sees B cause A. The causal arrow is fixed. This is what the Alexandrov topology captures. The topology of spacetime, the way regions are connected, the way points cluster, the way paths can be drawn, can be recovered entirely from the causal order. You do not need coordinates. You do not need a metric. You do not even need to know the dimension of spacetime. You only need to know which events can influence which others, and from that, you can reconstruct the topology.
If the spacetime is strongly causal, if there are no closed causal loops, no paths that return to their own past, then the Alexandrov topology coincides with the manifold topology. The causal order is the structure. And the Alexandrov-Zeeman theorem goes further. It says that if you preserve the causal order, you preserve almost everything. Any map that takes light cones to light cones without reversing their orientation must be a Lorentz transformation combined with a translation and a dilation. The causal order determines the metric up to a single overall scale. The geometry of spacetime, the distances, the angles, the curvature, is almost entirely fixed by causality. Before and after are not labels painted onto a pre-existing geometry. They are the geometry. That means punctuality is not about time in the everyday sense. It is about causal structure. When you arrive at the meeting, your world line intersects the meeting's world line at a specific point in space-time. That point has coordinates, and those coordinates are frame-dependent, but the intersection itself is invariant. Every observer agrees that it happened, and every observer agrees on the causal order. The meeting started, and then you arrived. That then is not a flowing river. It is a geometric relationship, fixed in the structure of space-time, as unchangeable as the fact that the corner of the room is north of the door. But if the structure is fixed, does it follow that the future is fixed as well? Only if you add the assumption that the structure is complete. Only if you assume the block contains all events, past and future, laid out in a static four-dimensional whole. And that assumption is not forced by the geometry. The geometry tells you that if two events are both real, then their causal order is invariant. It does not tell you that all events are real. It does not tell you whether the future exists. This is the gap the Stein rebuttal exploits. Stein showed that you can define a becoming relation in Minkowski spacetime that respects the causal structure. The relation is this: an event is definite as of a point if and only if it lies in the past light cone of that point. Everything else is not yet definite. The present is not a hypersurface cutting through spacetime. It is a light cone attached to each point, growing as you move forward along a world line. And the future, the events outside the light cone, is not yet real. That picture is minimal. It does not give you a global present or a universal flow. It gives you a local present, one for each observer, and those presents do not align. But it preserves the distinction between the definite past and the open future, and it does so in a way that respects the relativity of simultaneity. The Reit-Dijk-Putnam argument fails because it assumes simultaneity is transitive, and it is not. Stein's present is the smallest structure you can build that respects both relativity and becoming. Whether that counts as real becoming is debated. Some philosophers say yes, because it preserves the asymmetry between past and future. Others say no, because the present is so minimal, collapsing to a point and its backward light cone, that it barely resembles the flowing now of experience. But the point is that the geometry does not rule it out. The relativity of simultaneity does not force the block. It only rules out a naive global present. And that leaves the question open. If the future is not yet real, then the meeting at 3 o'clock does not exist until the present reaches it. You can be late, not because you failed to intersect a pre-existing point, but because the meeting came into being before you arrived. If the future is already real, then the meeting is a fixed point, and lateness is a geometric relationship, not a temporal one. The geometry does not tell you which picture is true. It only tells you what the structure looks like if one of them is true. What it does tell you is that the structure has limits. The past is not infinite. The BGV theorem proves that any expanding spacetime has a past boundary, a point beyond which geodesics cannot be extended. The boundary is a mathematical fact, derived from the assumption that the universe expands on average, and the expansion is confirmed by observation. We measure it in the Hubble constant, in the redshift of distant supernovae, in the acoustic peaks of the cosmic microwave background. The universe is expanding, and it has been expanding for at least 13.8 billion years. The BGV theorem says it cannot have been expanding forever. There is an edge. What lies at the edge is unknown. It could be a singularity, a point where density and curvature become infinite and the equations break down. It could be a quantum transition, a boundary where space-time itself dissolves into a more fundamental structure. It could be a bounce, a moment when the universe contracted to a minimum size and then rebounded into expansion. Or it could be the beginning of time, a moment before which there is no before. Vilenkin interprets it as a beginning. He writes that cosmologists can no longer avoid the problem of a cosmic origin, but others are more cautious. The theorem proves incompleteness, not genesis. It says the classical description fails at the boundary, and new physics is needed to describe what happens there. That new physics has not yet been found, and the boundary raises a question the block cannot answer. If the block is static, containing all events from the initial emergence to the far future, then the block exists as a completed whole. It does not come into being, it simply is. But then the question is, why does it exist at all? You cannot answer that question by pointing to something inside the block, because the block is everything. And you cannot answer it by saying the block arose, because arising is a temporal process, and the block is outside time. The only options are to say the block is a brute fact, unexplained and inexplicable, or to point to something outside the block that grounds it. That is not a question physics can settle. It is a question about existence itself, about why there is something rather than nothing. And it sits at the boundary between science and metaphysics, unresolved. But within the block, within the structure we can measure and test, the evidence is clear. There is no universal clock. There is no global present. Simultaneity is relative, time dilation is real, causal order is invariant, and the geometry of spacetime is built from the relationships between events. Those are facts, tested and confirmed. What they mean, whether they imply a static block or a growing process, whether time is emergent or fundamental, whether the future is real or open, is not yet decided. The geometry is neutral, the ontology is contested, and the question of whether you can be late to a meeting in any absolute sense depends on which interpretation you choose. Let me bring this exploration to a close. You began with a simple belief that you could be late to a meeting because the meeting had not yet happened, and whether you arrived before or after it depended on the flow of time. That belief rests on the assumption of a universal present, a single cosmic now that everyone shares, and a future that is genuinely open, waiting to be reached. Relativity denies that assumption. There is no universal present. Simultaneity is relative. What counts as now depends on how you move, and two observers passing each other on a sidewalk can inhabit presence separated by days at galactic distances. The natural interpretation, the one most physicists adopt, is eternalism. Past, present and future are equally real, arranged in a four-dimensional block, and the flow of time is a feature of observers embedded in the structure, not a feature of the structure itself. In that picture, the meeting is not waiting to happen. It is a fixed point in space-time, and your arrival is another point, and the relationship between them is geometric. You cannot be late in any absolute sense because there is no universal clock against which lateness is measured.
There is only the invariant fact that your world line intersects the meeting's world line at a point where the meeting has already started, as measured by any clock you carry. But eternalism is not forced by the evidence. The geometry is compatible with becoming. Stein showed that objective becoming is definable in Minkowski spacetime. Ellis and Rothman argued that the block grows, crystallizing into definiteness at the present. Sorkin and Dowker proposed that spacetime is discrete and that new elements come into being one at a time. Gisin argued that classical mechanics is indeterministic if real numbers are not physically real. Smolin argued that time is fundamental and the laws evolve. Each of these frameworks is compatible with the causal structure relativity gives us. Each preserves the invariance of causal order while allowing for real becoming. The evidence does not choose. What the evidence shows is that the everyday picture of punctuality is wrong. You are not racing through a universal flow toward an event that has not yet occurred. You are tracing a path through spacetime, and the meeting is another path. And whether those paths intersect at the agreed coordinates is a fact about geometry, not about a cosmic clock. The structure is causal, invariant, and deeply strange. It permits no universal now, no preferred frame, no absolute simultaneity. It leaves the ultimate question, whether the future is real or whether it comes into being, honestly open. If you found value in this exploration, consider subscribing. It helps these deep dives reach more curious minds. Sleep well tonight, knowing that every meeting you will attend is either already fixed at a point in spacetime you have yet to reach, or waiting to crystallize into existence the moment the present arrives. And the universe, for all its precision, has not yet told us which.